Welcome to LogiCal After Dark. Yeah, it's going to be exciting. Sean Carroll is our next speaker. His questions, the talent he would want instantly to have at his availability, to either be a fantastic poker player or a fantastic bass player, maybe at the same time. I think that'd be great. The thing he would save out of his house, I thought this was really interesting, an early edition book of poems by Baudelaire, which is illustrated by Rodin. Yeah, the guy that fought Godzilla, that guy. Ninjas versus pirates. This is our second vote for ninjas, because he said ninjas are invisible. It's fantastic. And pie versus cake, he said there's no contest. The best pie versus the best cake. Pie wins every time. Pecan, preferably. So, the big picture on the origins of life, meaning, and the universe itself. Please welcome Sean Carroll.
Thank you, George. Thank you, everyone. Thanks to all the organizers for having me out here. When I'm invited to do a keynote speech of some sort, of course, the first question one asks oneself is, how many people said no before they invited me? But I'm very glad that it worked out this way. And of course, it's always great to see on a Saturday night in Los Angeles, your idea of the best possible thing to do is to hear a talk about science and cosmology. Now, I know that given the title, there are certain automatic reactions. The title of the talk is the title of a book that I've recently written, The Big Picture, on the origins of life, meaning, and the universe itself. I want to start by saying I do not know what the origin of the universe is, what the origin of life was, or what the meaning of life is. That is not what I'm here to tell you. There's a long, venerable tradition of physicists, I'm a physicist, physicists like, especially after a certain age, to look around the intellectual landscape and see other fields of inquiry that are not physics and go, I could do that better than they can. I'm a physicist. How hard can it be? This is not what I'm here to do. I am not going to give you definitive final answers about any of these things, but I do think that there is a common vocabulary, a common ground in which we can discuss these various issues, and that's really what I'm here to talk about. So I want to start with a simple question that is related to physics, but one that also is related to our everyday lives. We want something to move, or we want to think about motion, how motion works in the universe. What are the properties that motion has? This is exactly the kind of mind-bogglingly boring question that you would be asking in an introductory physics class. Imagine you were asking this in an introductory physics class 2,500 years ago. So you don't know modern physics, okay? You're Aristotle. You're trying to think about how motion works. So I'm actually going to do an experiment. We're going to use the empirical scientific method here in real time. I feel like Faraday giving the lectures in the Royal Institution. So here you have an object. I don't know if you can see the object. The object is a bottle of water. I'm putting it on a surface. I'm going to look at the object and see whether it moves. Nope, it didn't move. We could wait longer, but it still wouldn't move. Now I'm going to see what happens when I push it. There you go. It moved. That's not fair. Thank you. Once again, professional physicist. Don't, think you could do this at home. But I want you to notice two things. Number one, it moved when I pushed it. And number two, it stopped moving when I stopped pushing it. These are not illusions. This is the real behavior of physical stuff in the universe. So Aristotle says, I know what's going on. Motion is an unnatural state of being. There are natural ways for things in the universe to be, places that things want to be in, forms of motion that places and things want to have. And if you just let something go and don't disturb it, it will just sit there, it will not move. Motion requires an impetus, a mover. Something needs to be pushing it. This illustration, stolen from the internet. The dog is not actually moving the car. You see the dog there, right? If you look very closely, there's a dog driving the car. But the point of the picture is, if you want your car to move, you have to cause it to move somehow. So Aristotle goes from this, and he's not wrong, right? We did the experiment. It's true. When I stop pushing, it stops moving. He's not wrong. Aristotle gets a whole physics and even a metaphysics out of this. Not only does motion require a mover, but you can go from that to say, well, there's lots of things moving in the universe. Every one of them requires a mover. For every effect in the universe, Aristotle says, there is a cause. He develops an elaborate metaphysics of different kinds of causes and effects. And he says, I don't believe that there are infinite chains of causes, so there has to be a first cause, an unmoved mover, and that's God. So he proves the existence of God. There you go. This is there was a mistake in that proof, which I'll get to in a second. We've made progress. But for a long time, this was a tradition, right? This was in the philosophy literature, this idea that how the world works, is a story of causes and effects. Aristotle, as we said, had this idea that there were causes and effects, and sometimes this is phrased in terms of purposes. There's reasons why things exist, reasons why things happen. And this was elevated to a principle called the principle of sufficient reason. The principle of sufficient reason is literally the bumper sticker you see that says everything happens for a reason, okay? There's a technical way of saying it that Leibniz, the guy on the right, said. Spinoza is in the middle. All three of these philosophers promulgated this principle, and the way that Leibniz put it was, the sake for which something happens is the final cause. Sorry, the principle of sufficient reason is nothing is without a ground or reason why it is. All right, everything happens for a reason. Now, you might have thought that the ultimate purpose, given the illustration we have here, is that philosophers should have ever more elaborate hairstyles. Up to the point where there was clearly some artificial enhancement by the time of Leibniz. But it turns out that the tradition did not continue all the way. And this is something where we physicists haven't spread the word very effectively. But this is not the way the world works. The world does not work as a system of causes and effects. You can still hear most people on the street, if you ask them, are there causes and effects in the world? Are they fundamental? Are they irreducible and like really part of the fundamental nature of reality? They would say yes. Those people are not right. I mean, the people who would answer you would say yes. Many people would look at you weird. Some philosophers have tried to spread the word. Here's Bertrand Russell, famous hero for atheists and skeptics. And he's not listening, but go ahead. Russell tried to spread the word that cause and effect is not part of the fundamental architecture of reality. We've been taught that by modern physics. So he says, the law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age. Surviving like the monarchy, he just couldn't help himself, right? Even when he's talking about metaphysics, he needs to dig the monarchy. Only because it is erroneously supposed to do no harm. Okay? So I'm not telling you that causes and effects don't exist. I'm not telling you they're illusions. I'm telling you they're not fundamental. They're not built into, and I'll explain exactly what I mean by this, they're not built into the deepest, most comprehensive, most fundamental vocabulary we have for talking about the world. And yet, the bottle of water stops moving when I stop pushing it, right? So the task of this talk is to reconcile those two facts about the world. On the one hand, you have the deepest level that we now know of describing the fundamental nature of reality. There are no causes and effects, as Bertie told us. But in the manifest world, in the world we live in, the world we see, in Aristotle's vision of the world, he was not wrong. You do need to push things to get them moving. How do you reconcile those? So a philosopher, Wilfrid Sellars, proposed two terms to describe these different ways of looking at the world, the manifest image and the scientific image. The manifest image is the world we live in, the world of our everyday experience, what we see in front of us. The scientific image is the deeper way of talking about reality that is revealed to us by scientific investigation. And unsurprisingly, in retrospect, not only do we learn things by doing science, but we realize that the best way of talking about the world at the deepest level uses a completely different vocabulary, a completely different set of concepts than the manifest image that we use in our everyday lives. So in the manifest image, you have the flow of time as being fundamental. In the scientific image, you don't. In the manifest image, there's this idea of causes and effects, the principle of sufficient reason. In the scientific image, that's nowhere to be found. Life and consciousness and thinking in the mind are somehow fundamentally different in the manifest image, but science says that's not true. Things like purpose, meaning, and morality are objectively given from somebody or something in the manifest image. Science says, once again, it's a little bit more subjective than that. It's very subjective in this slide because the font got cut off. So it just says purpose, meaning, and morality are. I mean, that's not what it's supposed to say. It's supposed, I forget, I'm going to translate it. Really?
It moved over, yeah.
Oh, personal.
Also, the universe has moved.
Personal. The universe tends to do that. For every event, there is a universe. All right. Should never let people put my slides on their computers. Okay. All right. So the purpose of my talk, if you believe that purposes exist in the manifest image in which we're experiencing right now in front of us, the purpose of my talk is to help explain how we reconcile these images of the world. And it's an incomplete story. There's still a bunch of work to be done. I think that there's very, very good reasons to think that our manifest image is utterly compatible with the scientific image once we dig into it carefully enough. So the story goes back many years. The event that I like to point to is 1000 AD, 1,000 years ago, the Islamic Golden Age, a Persian thinker named Ibn Sina, whose name was sometimes Romanized to Avicenna. This is a picture of him. It's not a photograph, but it's an engraving. And Ibn Sina, as a modern theoretical physicist, Ibn Sina to someone like me is enormously annoying. And the reason why he's annoying is because he was not a professional physicist. He was a doctor. Health and biology at the time, 1000 AD, were that's what he cared about. That's what he mostly wrote books about. On the weekends and in his spare time, he invented fundamental new laws of physics, okay? Very annoying to me as a modern professional physicist. One of the points that he made was what we now call conservation of momentum. It wasn't exactly in a modern vocabulary, so you can debate whether it really counts as conservation of momentum in the modern sense, but it was a crucial step along the way, because what Ibn Sina mentioned was that really the reason why the bottle of water stops moving isn't because of the fundamental nature of motion. It's because there's a force that is acting on it by the stool that it's sitting on. And he made the point that if you thought there was such a thing as the vacuum, as empty space, which he didn't think, it was a thought experiment, but he said if there were empty space, if there's just something moving in empty space, it would move forever at the same speed without anything pushing it. These days we build stuff like that, right? This is a spacecraft, this is Voyager, flying through interstellar space, and it just moves at a constant rate. And of course, people like Galileo and Newton codified these kinds of ideas into what we call the classical mechanics, the modern precursor of modern physics. So that's, on the one hand, a very specific physical principle that is very useful to physicists because we can use it to torture undergraduates when they take their physics course in college. Inclined planes, frictionless surfaces, all of that stuff. But on the other hand, it's not just a little principle, it is a fundamental difference in how we think about the world. It is not just trading one equation for another, it is trading the set of concepts that we rely on for a completely different set of concepts. If things can just keep moving by themselves, if the thing that happens naturally is that something that is moving just keeps moving, then you pull the rug out from underneath the idea that that thing needed a mover, that thing needed something pushing it. If the world, the universe, can just keep moving by itself, then the whole argument for the unmoved mover or the first cause begins to go away. It became a little more obvious in the hands of Pierre-Simon Laplace, circa the year 1800. Now, Laplace didn't invent classical mechanics. That was Newton who did that long before Laplace. But Laplace arguably was the first person to really internalize the lessons, the implications of classical Newtonian mechanics. So think about this experiment on the left-hand side. These are billiard balls scattering off of each other, and these are physicist billiard balls. So there is no noise, no friction, nothing like that. They can just go their own way with conserving momentum. And Laplace says, look, ordinarily, were you to give this as a problem to a first-year physics student, and you say, here are these billiard balls, they're coming in with a certain velocity at a certain distance and angle, what happens to them? It's what we call an initial value problem in physics. You give me what they are doing, I will tell you what they're going to do in the future. But what Laplace says, if you dig into the equations that Isaac Newton has handed down to us, you don't need to give us the information about the billiard balls at the start. You could tell me what the billiard balls were doing at the end of that experiment. The Newtonian laws of physics are 100% reversible. The information contained in what the balls are doing at the end of the experiment is enough to wind the clock backwards and tell you where they came from. Indeed, the information you need to say what this physical system is doing is absolutely equally there at every moment of time. This is something that modern physicists call conservation of information. So Ibn Sina and his friends handed down to us conservation of momentum. Laplace is pointing out there's a much more profound idea underneath this. The world is fixed by the data that exists in the world at any one moment in time. That completely determines both the past and the future. What that means is that the way of thinking about how the world works isn't a story of progress toward a future goal. It's not teleological. All the information is there at every single moment. What that means is that the laws of physics are not something that says this, then this, then this, then this in some direction of time. Rather, they are a pattern. So think about the numbers, the integers on the real number line down there at the bottom. -1, 0, +1, +2, +3. You understand that if I give you a number, 7, you can tell me the number to the left of it and the number to the right of it, 6 and 8, right? But no one says, oh, 6 is the cause of 7 coming into existence. That's just not how it works. There's a pattern that relates the different numbers to each other. Laplace's point is that physics works that way. The universe works that way. There's no cause that relates what happens at one moment to another. There's just a pattern given to us by some equations, the laws of physics. He even envisioned a vast intellect, which we now call Laplace's demon, that could know everything in the universe at any one moment. And he says to that demon, he said to that vast intellect, he was an atheist, he didn't believe in demons. He said the past and future would be as immediately knowable as the present moment. Now, you might say, well, we know better than Laplace in terms of what the laws of physics actually are, right? We've moved beyond particles bumping into each other in this simple way. And that's true. Here are the current laws of physics. This is the dramatic claim that I want to make. The laws of physics underlying our everyday lives are completely known to us right now. This is a claim that Laplace could not have made. And I want to emphasize that every word in that sentence is important. You can't throw away one of the words and then complain that the sentence is no longer true. That would be correct. All the words matter. So what do I mean by this? I mean, in your body, there are atoms. There are particles, right? Physicists know how to describe what atoms are. Here's the cartoon version of an atom. There's quantum mechanics involved. It's more complicated than this. But this is the fairly accurate representation of what the ingredients are. We know that atoms have a nucleus in the middle and an electron going around. The nucleus of an atom consists of protons and neutrons, two different kinds of particles. And in turn, those protons and neutrons are made of quarks, up quarks and down quarks. So roughly speaking, there's three kinds of particles that are relevant. There's a fourth, the neutrino, that can be created by certain subatomic processes. So really 4 particles. And all of the interactions between these particles come down to 4 different kinds of forces. The electromagnetic force is what holds the electron to the nucleus. The strong nuclear force holds those quarks together inside the protons and neutrons. The weak nuclear force converts up quarks and down quarks to each other and spits off neutrinos in the process. And gravity pulls everything to everything else. That's it. 4 forces and 4 particles. In the background, there's a Higgs field pervading all of space. If you poke the Higgs field, it starts vibrating, and you see a little particle called the Higgs boson. We first successfully did that in 2012. Big news in Geneva, the Large Hadron Collider. We discovered the Higgs boson. There are other particles that exist that we know about, but they're just heavier cousins of these particles. So there's not only an electron, there's also a muon and a tau. There's not only an up quark, there's a charm quark and a top quark, etc. All those heavier particles, if you made one right here, it would decay away. In an instant, it would make these particles. So the claim is, you and I are made of these particles. That's the easy part of the claim. The hard part, there's 2 hard parts. Number 1, these are all the particles we're made of. There's no particles that are not on this picture that exist and play an important role inside you. Number 2, we know what these particles do. We know the laws, we know the rules, we know the equations that they obey, and no future physics experiment is going to say that we need a modification of those rules to explain what happens inside you and me. The laws of physics underlying our everyday lives are completely known. And the everyday lives bit there is crucially important because there's obviously an enormous amount of physics that we don't know. We don't know what dark matter is. We don't know what happens inside a black hole or at the Big Bang. We don't know what happens when complicated collections of particles come together to make complicated molecules or biological cells or political systems for that matter. So there's various higher levels of description we don't understand. That's why the underlying is important here. The laws of physics underlying our everyday lives are completely known. Now, part of the purpose of a meeting like this is what we call skepticism, so you shouldn't believe me. You probably don't believe me. I'm going to give you a tiny little bit of evidence that this claim is actually true. The first bit of evidence is mostly rhetorical because you see a picture like this, it doesn't look very impressive. You're like, I could have drawn that. My kid could have drawn that. It's just a cartoon. I'm not going to believe your physical theory unless you show me the equations behind it. Well, here you are. This is the equation. This is what Nobel laureate Frank Wilczek has dubbed the core theory of modern physics. It consists of two parts. It is general relativity, Albert Einstein's theory of gravity, and the standard model of particle physics. You may have heard, depending on what street corners you hang out on, that gravity and quantum mechanics don't get along very well, but actually that's an exaggeration. The more careful statement is we do not have the complete and once and for all final theory of quantum gravity, but as long as you restrict yourselves, once again, to our everyday lives, to certain regimes of energies and speeds, we have a perfectly good theory of quantum gravity. If you want to explain the Earth moving around the sun or the moon moving around the Earth or SpaceX launching things into space and landing them using quantum gravity, you can do that. We have the right theory. So my claim is that this equation governs what is happening in this room right now, and no future discovery in physics will change the fact that this equation suffices to do exactly that. You notice that if you look closely, I'm not going to go into all the details. You can ask questions about the i's and the pluses and the minuses. The equation is our modern version of what Laplace's demon would have in mind. Laplace's demon had Newton's equations in its mind, and it would say, given the universe right now, what happens next? This is the modern quantum field theory version of that. You give me the quantum state of the universe right now, this is the equation that tells you what happens next. It is not teleological. It is not moral. It does not care what you do. It does not judge you. There is no goal or purpose towards which it strives. There's no causes and effects in this equation. It's just a pattern, just like 6, 7, 8, 9, 10. Now, you might object. A slightly more sophisticated version of the previous objection is, okay, you have equations, but I don't believe that your equations are truly fundamental unless they can fit on a T-shirt. So I prove to you that that can happen. Once again, an experimental demonstration. You can buy the T-shirts on my website. I don't make any money. There you go. Okay. The real objection you should have is, even if you're scientifically open-minded and you think that physics is more or less on the right track and you believe in atoms and so forth, you're trained by your skeptical upbringing to say, but surely there could be future experiments that lead us to change our theories, right? Now, on the one hand, strictly speaking, yes, of course, because that is always true. Science doesn't prove things. You never reach a point in our confidence in empirical statements given to us by science where it's 100%, because that would mean that no new data could ever change your mind, and that would be bad. But you do reach a point where it is a waste of time to worry about the prospect that your mind will be changed, and I'm going to try to make the case that that's the case for the core theory. And the reason why, so I'm really trying to say something very, very specific about the form of this particular physical theory. It's not just that it fits the data we have right now, but this particular kind of theory built into itself its own limits of applicability. Not only do we know what the theory says, we know how far we can extend it before it should fail. And let me just give you one slide's worth of argument in favor of this. There's a feature of quantum field theory called crossing symmetry. And I'm going to explain to you what this means. This picture we have here is called a Feynman diagram. my claim to fame in the physics community is that I sit at the desk that Richard Feynman used to sit at Caltech. Yes, thank you. The rule is that Feynman's old desk goes to the most senior theoretical physicist at Caltech who is not senior enough to get a brand new desk when they arrive. That's me. And the Feynman diagram is perhaps one of his most famous contributions to physics. What the diagrams do is tell us not only what can happen to elementary particles, but they give us a way of calculating the likelihood, the probability that this kind of thing is going to happen. So what you do is you read from left to right. Time flows from left to right. The picture on the left imagines that there's some kind of new particle that you haven't yet detected in red, and there's some kind of ordinary particle, an electron or a proton. Okay? You hypothesize maybe there's a new particle. Maybe there's a Zilbot particle that is really, really important for human consciousness. It plays a role in how our brain works and brings to life qualia and human experience, and you, physicists, with your narrow-minded materialistic perspective, haven't discovered it yet. But we're going to trust quantum field theory to describe what it would do, okay? So if that were true, then there would have to be an interaction between this new particle and the old particles. If you have a bunch of new particles that you invent that don't even interact with us at all, then who cares? They might exist, but they don't affect our everyday lives. Indeed, there are such particles. Dark matter is exactly such a particle. We believe there are dark matter particles in the universe. Most of the mass of the universe by energy is dark matter. We believe that there are probably millions or billions of dark matter particles flying through this room right now. And we don't care because they go right through. They do not interact with us. To affect our everyday lives in any way, this new particle would have to interact substantially with the particles that we know are in us, like electrons, protons, and neutrons. So imagine there's some new interaction. There's a new particle that interacts. Hypothesize that. Crossing symmetry, part of the Feynman diagram technology, says that if this diagram exists, and you can calculate how important it is, you can rotate the diagram by 90 degrees. You get another diagram that also exists and is just as important, is just as probable, just as likely. So you rotate our diagram by 90 degrees clockwise, and what you get is two ordinary particles coming in, annihilating and producing two of these new particles. In other words, it is built into the fundamental features of quantum field theory that if there exist new particles that could interact with the existing particles in your brain, then we could make them. All we have to do is take the particles that we already know about and smash them together and see what they make. This is the favorite leisure time activity of experimental particle physicists, smashing together particles, seeing what comes out. That's how we discovered the Higgs boson. We have smashed together every kind of particle you can imagine. We've smashed together electrons, positrons, neutrons, protons, the whole bit. And we've cataloged everything that has come out. Nothing that has come out of what we've looked at can possibly play any role in our everyday lives. Either they're too heavy, and therefore you can't make them, or they just disappear in a zeptosecond. The lifetime of a Higgs boson, for example, is 1 zeptosecond. That is a very short period of time. So the point is not just that we haven't yet found anything in physics that could play an important role in your brain. The point is that we have very strong reason to believe in the fundamental principles of quantum field theory. It is really the only way of reconciling the principles of quantum mechanics with relativity. And if you believe in quantum field theory at all, then quantum field theory tells you that had there been any new particles or forces that could have affected your everyday life, we would have seen them already. And we have not seen them already. So whatever unanswered questions there are about the manifest image, about the lives that we lead, about our psychology and biology and so forth, and there are many unanswered questions, we are not going to answer them by appealing to new laws of fundamental physics. The core theory is still going to have to be the basis of whatever explanations we come up with. And that process of coming up with such explanations involves this idea called emergence, the relationship between the microscopic theory, the foundational comprehensive theory at the bottom, which these days we would say is, to the best of our knowledge, the core theory, There could be something underneath it, that's fine, but there's also something on top of it, the many different layers of macroscopic emergent reality. It's the macroscopic world that is populated by tables and chairs, people and planets. The microscopic world is populated by particles and forces and wave functions, and emergence matches what happens at one layer to what happens at the other. So there's many different ways of talking about the world. There's one world, the natural world, but there are many different ways of talking about it. And not only are the actual vocabulary words different, but the fundamental conceptual frameworks are different. So if you look at the microscopic world over there, again, it's as Laplace said, there are patterns of nature. There are differential equations that tell us what happened. There's conservation of information. It's a wholly different story in the macroscopic world of the manifest image. There's a difference between past and future. There is cause and effect. It is true that I need to push the bottle to keep it moving. There are reasons why things happen in the macroscopic world. So how do we connect these different levels? That's the difficult part. That equation I showed you, the core theory equation, that's the easy part, okay? This is the hard part. That's why we're not done with it yet. So let me give you a little bit of a clue. So the rest of the talk is much less firmly founded in the sense that now the easy part of science is that equation I showed you for the core theory. That's very rigorous and very established. And the higher up we go in layers of emergence, the less we understand and the more conjectural we have to be. So I can't make an airtight case from now on. I'll try to make a plausibility case that the world we see is completely compatible with this story. And it begins with the arrow of time, with the fact that even though it is nowhere to be found in the fundamental equations of physics, there is manifestly a difference between the past and the future in our everyday lives. There's many different ways in which this difference manifests itself. For example, you remember what happened yesterday. You don't remember, I hope, you don't remember what will happen tomorrow, okay? There's a difference in your causal powers to affect the world. Again, in the macroscopic everyday world, you can choose right now to get up and leave. You can say, this is a boring talk, I don't like it, I'm going to walk out. You have that ability. You cannot choose right now to not have come to the talk, right? You have a different access to the future and the past somehow. In basic physical terms, we talk about entropy increasing, entropy being a measure of disorderliness, disorganization of the universe. Entropy goes up as time goes on. You can start with orderly things like an unbroken egg, and you can break the egg. That's easy. You can scramble it. Putting the egg back together, much, much harder, and will never happen all by itself. So the physicist's idea of the origin of time asymmetry in all of its different manifestations is what we call the second law of thermodynamics. The first law is boring. It says energy is conserved. Second law, very interesting, it says that entropy increases in isolated systems as time goes on. Now again, this difference between past and future is not built into that equation that I showed you. It is nowhere to be found in the fundamental laws of physics. There has to be something about the macroscopic world that gives us this difference between past and future. What could it be? Well, the answer is that the arrow of time is very much like the arrow of space. You might not think that there is an arrow of space, but if I were to let go of this, I should have predicted. It's more impressive when you predict the future before it happens, but I predict that when I let this go, it will fall down and not up. There you go, science. Thank you. Now you know that's clearly an arrow. That's clearly a difference between up and down in our everyday world right here, right? But no one goes around writing books about the arrow of space as if it's some big mysterious thing. You know why. It's not the fundamental laws of physics. It's because we live in the vicinity of an influential object, the Earth, right? It's the Earth's gravitational field that pulls the bottle down. If you were out there in space, if you were an astronaut, you let the bottle go, it wouldn't move, right? There'd be no difference between up and down. There's no arrow of space out in the middle of, in between the planets where there's no gravitational field. The modern viewpoint is that the arrow of time is exactly the same way. Just as the arrow of space can be traced to the fact that we live in the vicinity of an influential object, the Earth, the arrow of time can be traced to the fact that we live in the aftermath of an influential event, the Big Bang. 13.8 billion years ago, the universe was hot, dense, and smooth. You go through the equations, you figure out that's very low entropy. The early universe started with an extraordinarily orderly state. If you want to know why, I can't tell you that. That's a whole different book, a whole different talk. We don't know why. We have ideas. But it's a fact, it's an empirical fact, that our universe started near the Big Bang in a very, very, very special state for some reason. The universe is like a little wind-up toy that was all wound up and ever since then has been puttering along, winding down. Not just the last 14 billion years, but many, many billions of years toward the future, we believe, will be a story of increasing disorderliness, increasing entropy of the universe. That's why there's a difference between the past and the future, because there is a boundary condition in the past. Aristotle and his friends got it exactly wrong. They thought that the world was teleological, headed towards some future goal. The future is completely irrelevant to the universe. The universe is unbalanced in time, not because of the future, but because of the past. It started in a special state. It is econological, not teleological. So let me just give you one tiny example of how that works. It's easy to say, I can break eggs and not unbreak them. It's harder to explain cause and effect or memories, but you can do it. The reason why you can remember yesterday but not tomorrow is because the entropy of the universe was lower yesterday. Why was it lower yesterday, the entropy of the universe? Because it was even lower the day before yesterday. And the reason why that is because it was even lower, and it goes all the way back to the Big Bang. So let's explain what I mean by that. That's why you remember yesterday, because the entropy was lower. And it has nothing to do with the intricate, specific mechanisms of the human memory system. This picture right here, an egg broken on the sidewalk. When physicists start talking about entropy, they like talking about broken eggs. Broken eggs and mixing cream into coffee, that's going to come on the slide or two. This is a memory. I claim that this egg stands in for what you mean by a memory. What do I mean by that? I mean, if you walked down the street and you see a broken egg, you could ask yourself, well, I wonder what the future of the egg will hold. You're in a contemplative mood. And there's many possibilities, right? The egg could just sit there and fester. A dog could come by and eat it. It could wash away. Someone could clean up. There's many different open possibilities about the future, as far as you know. But if you thought to yourself, I wonder what the past of the egg held, if you're on your toes, you can say with a pretty high degree of confidence, I bet there was an unbroken egg that somebody dropped, right? This is very, very likely. What gives you that such stronger hold on the past given that current information? It's not the fundamental laws of physics. You have some data, some information about the universe. There's an egg sitting on the sidewalk. If all you knew was that equation of the core theory or Newton's laws or anything like that, and you ask yourself, given that information, what would the past of the egg hold and what would the future of the egg hold, there would be just as many possibilities for the past or the future. But there clearly are not in the real world, and the reason why is because ever since you were a kid, you secretly knew that the Big Bang had a low entropy. That there was a low entropy boundary condition that breaks the symmetry between past and future, and therefore when you reconstruct the history of the egg now, in the future you don't know what's going on, but in the past you know it had to start in this low entropy condition, and that picks out certain plausible histories in between the Big Bang and today. Given the existence of the egg on the floor and the existence of the Big Bang, it was highly likely that that egg came from an unbroken egg. And all of your memories, all of your artifacts, all of the fossils in the geological record, all of your differences in your knowledge of the past and future are ultimately traced to this fact. Which is great, full employment for theorists, physicists, philosophers, chemists, understanding how entropy increases. If you, once again, hang around the wrong circles, you might know that this makes some people sad. The fact that entropy is increasing, the world is just getting more and more disorderly, that's a little bit depressing. Or if it's a little bit more focused, some people say, look, I'm not disorderly. I mean, occasionally I don't clean my room, but still, like, as a physical system of atoms, I am very, very exquisitely organized. You can't randomly rearrange the atoms in me and make it just as good. So if the universe's history is just one of increasing disorder, how does something so intricately ordered as a human being come to be? And there's a naive version of this and a sophisticated version of this. The naive version says entropy increases, the entropy of our biosphere has gone down, therefore it's incompatible with the laws of physics. We know that's nonsense. The second law of thermodynamics says that the entropy of closed, isolated systems goes down, and the biosphere is not in any sense a closed, isolated system. But there is a more sophisticated version that says, okay, fine, the Earth is not a closed system. It is allowed for entropy to go down here on Earth, but it doesn't explain to me why complex structures really did come into existence. Maybe it's allowed by the laws of physics, but why did it actually happen? And that's a very interesting story, and it comes down to the fact that there's a big difference between entropy and complexity. There is a naive, casual notion that low entropy systems are organized. Sorry, I should say the other way around. Organized systems, complex systems, are low entropy, and messy systems are high entropy. Therefore, you think, well, as entropy increases, complexity goes down. But that's just not thinking about what you mean very much. I'd like to give this example of cream mixing into coffee. Okay, it's the standard example of entropy increasing. All the cream's on the top, all the coffee's on the bottom. You mix them together, they get mixed up. That's easy, the arrow of time at work. You're not going to be able to unmix them. Put your spoon in there and try your best. You're not going to separate the cream from the coffee, okay? Entropy has gone up. But think about the simplicity versus complexity here. In that first picture, with all the cream on top, all the coffee on the bottom, that's a very simple picture. If you want the mathematical manifestation of this, mathematically, there's something called the Kolmogorov complexity. It's basically how long you have to keep talking to describe the system, okay? On the left, you don't have to keep talking very long. All the cream's on the top, all the coffee's on the bottom. It's very simple. But also far on the right, you don't have to talk for very long. They're all mixed together. It's still very simple. It's in the middle, where the cream and coffee are mixing together, where there's tendrils of one mixing with the other one, where there's little fractal patterns and turbulence. That's when it's complex. Literally, if you took a picture of this on your iPhone and you looked at the file size of your image, the image in the middle would be bigger than the one on the left and right because there's less simplicity, there's more complexity there. It turns out this is a very common feature of the evolution of closed systems. When you start in a system that is very, very low entropy, it's often very simple. It will evolve inevitably to higher entropy, and it's in between that complexity first comes and then goes away. It's not just that the existence of complex structures here on Earth is compatible with the fact that entropy is increasing. It's because entropy is increasing that this is allowed to happen. The existence of complex structures like us is allowed by the fact that we live in a highly out of equilibrium environment where entropy is increasing. It's not just cups of coffee, the universe is like this. Here's the evolution of the universe in 5 simple slides. They always tell you about the past, they never tell you about the future. Let me tell you about the evolution of the universe. So on the left, that's a photograph of the universe 1 second after the Big Bang. It's not really a photograph. It's a white rectangle that I made in PowerPoint, but if you were there 1 second after the Big Bang, the universe would be hot, dense, smooth, and glowing very, very brightly. It would look white in every direction, okay? As time goes on, entropy increases, and how that manifests itself is first that structure forms. That second image, a few 100,000 years after the Big Bang, is an actual photograph. That's the leftover radiation from the Big Bang, the cosmic microwave background, and you see there's differences in temperature from place to place because there's differences in density. Gravity works to increase the contrast knob of the universe, pulling things together when they're overdense and moving them apart when they're underdense. So in the middle, you get today, this beautifully complex universe, planets, stars, galaxies, a very lumpy, inhomogeneous universe. But we know the universe is expanding, and we think it's going to expand forever. So those stars are going to burn out. Those stars are going to fall into black holes. The fourth picture is a picture of a black hole. And Stephen Hawking in the 1970s told us that even black holes don't last forever. They just evaporate away. So if you wait long enough, approximately 10 to the 100 years after today, the last black hole will have evaporated, and the universe will be nothing but empty space. Okay? It's not rebalance your stock portfolio kind of information. It's a very long-term fact about the universe, but that's the best current model that we have of cosmology. You see what's happening. On the left, low entropy, but very, very simple. On the right, high entropy, but again simple. The complexity of the universe comes in between. Now, all right, if you're with me so far, you're saying, okay, I used to worry that the increase of entropy meant that life shouldn't arise. Now you've convinced me that complexity can arise. But why did it actually arise? How did it actually happen? How did life itself actually come to be? And the answer, is that we have no idea. Well, not no idea. We have very little idea. We have some ideas. We don't know which of our ideas are right. I learned a lot about this. I started learning about this on an airplane. I was taking a flight. I was going to give a talk at a conference. And as I often do, I'm reading physics papers on the flight, right? And as a professional cosmologist, it often happens that I'm talking to people in the real world, and they realize I'm a professional cosmologist, and they would like to explain to me their theory of the universe. Okay? I usually try to not listen to that explanation, but you're on an airplane, so I'm sitting there on the airplane, I'm reading my physics papers. Actually, I was reading about statistical mechanics and the origin of life. The guy sitting next to me on the plane looks over and goes, "Oh yeah, I've read those papers. I know about that." He says, "In fact, I can tell you the purpose of life." I'm like, "Okay, how long is this flight going to be exactly?" But then I ask him, I say, "Okay, we have a long time. What is the purpose of life?" And he says, "The purpose of life is to hydrogenate carbon dioxide." Now, as it turns out, I was sitting next to Dr. Michael Russell from the Jet Propulsion Laboratory, one of the world's experts in the origin of life. And he does indeed have a theory. He is a leader of one of the camps in the origin of life debate called the Metabolism First camp. And this is what he meant by that story. He says, in the early days of the Earth, there were environments where, in the terms I've been using so far, the entropy was very low. In particular, there was a lot of carbon locked up in the form of carbon dioxide. Okay? It turns out, you go through the math, if you have a lot of water and a lot of carbon dioxide, that is a low entropy chemical state compared to taking the hydrogen away from the water, giving it to the carbon, and making methane, hydrogenating the carbon dioxide. So in principle, that carbon dioxide wants to become methane. It wants to become hydrogenated. The problem is, the point of this graph on the left is supposed to show you that even though it is higher entropy to be methane, all the steps along the way are lower entropy. So there's no simple path that takes you from carbon dioxide to methane, lowering the entropy along the way. What there are, wait for it, are complex paths, complex systems of chemical reactions that can work together to release the entropy pent up in that carbon dioxide. And Michael Russell's theory is that that is why life began, as a complex network of chemical reactions that was driven by the desire to increase entropy. And because he's a professional geologist, he actually proposed the existence of a very, very specific kind of geological formation, what is now called a warm alkaline thermal vent underneath the ocean. And he said if these existed and lasted for long enough, they'd be the perfect environment for life to begin. And as every scientist always wishes happens in their lifetime, after he made the prediction, it was shown to be true. They found exactly the kind of geological formation he predicted. This is the Lost City Formation underneath the Atlantic Ocean. There could be many, many more like that. We don't know whether this has any relationship to how life actually began, but it's a plausible theory for why it might have started, and it reminds us that the origin of life isn't antithetical to the fact that entropy increases. It might have been because entropy is increasing. We know that right now, that's what life is. If you believe in the core theory, if you believe that we're made of all these particles, life is not a substance. Some people used to think in the 1800s that life was a thing. Life was a fluid, a force that would move in and out of you, and when you died, it left you. We now know that life is a process. It is like a chemical reaction, like the burning of a candle. And when people ask you, well, where does your energy go when you die? You say, well, where does your energy go when you shut down your laptop? It's still there. It's just not doing the same thing that it was doing before. Here on Earth, I told you that we are not a closed system. The sun, what good is the sun to us here on Earth? And you might say, well, the sun gives us energy, and that's true. But we give the same amount of energy back to the universe. We get energy in the form of solar radiation. We radiate away the same exact amount. Sorry, we used to radiate the same exact amount. We now radiate away slightly less due to greenhouse gases, but that's again a different talk. The difference is that we get visible light and we radiate infrared. For every 1 photon of energy we get from the sun, we radiate 20 photons back to the universe with, on average, 1/20th of the energy each. And that means 20 times the entropy. The biosphere of the Earth is very organized and low entropy, but it is an entropy-generating machine. You photosynthesize, you make plants, you make glucose, you make ATP, you chew your cud, you write books, you go to conferences, and then you radiate all of this higher entropy stuff back into the universe. That's what we are. We are little creatures, little configurations of particles from the core theory that increase the entropy of the universe. Okay, the final question that people have, they're like, all right, good, you've totally convinced me that life is just a bunch of chemical processes. That's never happened, by the way, but it could over the years happen. But they say, what about consciousness? What about, I have a feeling inside me that you are never going to explain using your fancy math, okay? And again, just like life or the universe, we don't have the final answers here, and consciousness is arguably the hardest problem. It's very complex. It is exactly, if you believed in a purely naturalistic, physicalistic universe, human consciousness is exactly the last thing you would expect us to explain, because it's the hardest, most complicated phenomenon there is. What we might be able to do is sketch out some of the steps along the way. Here is a famous system. This is a model biological systems, C. elegans, the nematode, the flatworm, which is a wonderful thing because you can download an app called Open Worm, okay? What does this do? Well, we know that in our brains there are neurons. We think that the neurons have a lot to do with how we think and how we have memories and things like that. The problem is the human brain has something like 85 billion neurons and an enormous number of connections between them. The whole map of all the connections between the neurons is called the connectome, and we would like, as one of our big-ticket neuroscientific projects, to map out the human connectome. Meanwhile, we map out the connectome of the nematode. That's a lot easier. The poor nematode has 302 neurons. Okay, that we can do. In fact, we have done it, and this is what you can see on Open Worm. You can see every single neuron in the nematode and how it's connected to all the other neurons. That is not enough to let us read the mind of the nematode, but we can start asking questions. So there's a paper that came out, it's conjectural, I don't know how believable it is. There's a paper that came out that says we have figured out the role of one of these neurons in the 302. The role of this neuron is to distinguish the flatworm from not the flatworm. This neuron is the one that goes like the little nematode is moving around. It's like it sees something. Is that dirt or is that water or is that just my tail? Okay? That's the job of this neuron. Not that hard to imagine that functionality evolving in purely physical, naturalistic terms. Also, if you're willing to use your imagination a little bit, not that hard to imagine that was the first step towards self-awareness. The first step towards representing your own self as part of your mental construct of the world. That's me, that's not me, okay? It's a very tiny step, but perhaps a step along the way. Here's another step, millions of years later, again, completely conjectural, but Malcolm McIver, a neuroengineer at Northwestern, studies fish. And in particular, he studies how fish view the world. And he had, for better or for worse, he had a philosophical training as an undergraduate, so he thinks about the big picture here, and he says, you know, the thing about fish is they have eyes, but they can't see very far because they're underwater. The attenuation length of light in water is tens of meters. Even when things are very clear, you can't see very far. So you're a fish swimming at meters per second and you see something, you only have seconds to react. The evolutionary pressure is to see something and instantly say, you know, friendly, fearful, is it food, what should I do? Okay? But he says at some point, the first fish started crawling onto land, right? This is Tiktaalik, who crawled onto land. And once you're onto land, your evolutionary pressures change. In air, the attenuation length is essentially infinite. You can see the moon, right? You can see for kilometers. You can see things coming far away. So he says the hypothesis is there's a new evolutionary pressure because there's a new strategy that evolves. Develop the capacity to think about different hypothetical strategies before acting on them. So he says when you crawl up onto land, it pays to develop an imagination. What modern psychologists call mental time travel, the ability to project yourself into situations that have not yet happened. And they are currently, there's a new paper coming out like this week or next week. He made a prediction for how eyeballs evolved on the basis of this theory. It seems to be true. Again, we don't know whether this was an important step in the development of consciousness, but you can see how it might be. The point is not that we understand what consciousness is or where it came from, but we don't see any barriers to eventually understanding. What we do know is that the brain is made of the particles of particle physics. The brain is made out of electrons and protons and neutrons, up quarks and down quarks, held together by those forces, right? And they assemble themselves into atoms and molecules and neurons. I can give you evidence for this. You don't need evidence for this. You're probably pretty convinced already that there are atoms and particles in your brain, even though you've never seen them, right? So here's evidence. This is my brain. This is not to scale, the picture on the right there, but this is a view of my brain using MEG, magnetoencephalography, right? So this is in David Popple's lab at NYU. They put you in a big machine. They make you think something. He made me think by playing some beeps and boops, and my brain would go, yes, that's a sound, or no, it's not, okay? What does it mean when I say my brain goes? It means that there's a signal, a thought going in my brain, and if you're a physicalist, you believe that that means that there are electrochemical signals moving along the neurons and hopping from neuron to neuron, charged particles in motion. Any physicist will tell you when a charged particle starts moving, it creates a magnetic field. So if you think that a thought in your brain is a manifestation of particles moving in your neurons, then you make a prediction that a magnetic field should pop into existence in your head when you think a thought. And that's a magnetic field, that's a map of it, quadrupolar magnetic field, that pops into existence in my head when I heard this sound. Okay? Just a couple of millimeters outside my skull, the little magnetic field caused by my electrons moving. It's very exciting to me as a physicist that this actually works, these equations that we have. So no one denies that there are particles obeying the laws of physics in your brain. The question is there something else to it? Do we need more than that? So famously, this guy on the left, René Descartes, in the grand haired tradition of philosophers, thought there was something more than just the brain, that there was an immaterial soul. He was a dualist. We talk about Cartesian dualism. There is the body, which is physical and has a location, and he says there's also the mind, which is immaterial, that is not even part of the physical world at all. And back then, it was hard to get a tenured position back then in the 1600s. You wanted to be nice to wealthy people, so the woman in the middle, who is not nearly as famous as Descartes, but should be, this is Princess Elizabeth of Bohemia. She would have been a famous mathematician or scientist, but she was female at the time. Fortunately for her, she was a princess, so that gives her at least some opportunities, namely that the people who were famous philosophers would kiss up to you because they want the princesses to be on their side. So Descartes sent his works to Elizabeth and said, you know, Your Majesty, I don't know what the formal salutation was, please read my works. To his surprise, she wrote back saying, you know, I've read your books, and, you know, frankly, I think you could have done better. The thing that she was most skeptical about was this idea that there was a mind-body dualism, that you could describe a human being as a physical body located in space, but the mind is this ephemeral, non-material, non-located thing. And she had a very pointed criticism. She said, if that's true, how can this mind with no location in space possibly influence our bodies that certainly do? How can it push around our hands moving up and down? How can my immaterial spirit say, raise your hand now? So Descartes tried to come up with an answer, and that's the drawing he made over here on the right. They had started peeling people apart and looking inside. They knew that the brain was bicameral. There were two hemispheres. But Descartes was convinced there was only one soul. So he pinpointed the one part of the brain that looked like there was only one part of it, and that was the pineal gland. So that little teardrop-shaped thing there, the pineal gland, and Descartes says, this is it. This is the radio receiver that gets signals from the immaterial soul and tells our mind what to do. Nobody believed him, even then. And Princess Elizabeth was quite unconvinced. Today, the translation of Princess Elizabeth's critique in modern language is, we have an equation that says what the particles in your brain are going to do. You tell me, here's a particle, here is its surroundings in terms of here's the electromagnetic fields and the gravitational field and so forth. This equation says exactly what it's going to do. If you think there is more to what's happening in your brain than the laws of physics, that means you think this equation is wrong. You think this equation is violated by the behavior of particles in your brain. Tell me how. And no one has ever told us how. It doesn't mean it's not possible. That is the challenge you would have to overcome if you wanted to be a modern-day Cartesian dualist. All right, so I'm wrapping up, almost there. The story, the label that I give to this way of thinking in the book is called poetic naturalism. Naturalism is the idea there's only one world, the natural world, the world we learn about through scientific investigation. Poetic means, but there are many different ways of talking about the world. And in this sort of scientific presentation I've been giving you so far, from physics to biology to psychology and so forth, you can see how the different ways of talking would fit together and be compatible with each other. The story extends with some modifications to things like meaning and morality and purpose. These are also ways of talking that are not fixed in the same way as our scientific descriptions are. And I like this motto by Muriel Rukeyser, who's a poet, but she was not an anti-science poet. She was actually a big fan of science. She wrote a wonderful biography of Hosea Willard Gibbs, the famous American chemist. And she says, the universe is made of stories, not of atoms. Now, she knows perfectly well the universe is made of atoms, okay? The point she's making is, but we bring the universe to life by choosing to talk about it in different ways. If you meet a person for the first time, if you're on a blind date, you're sitting across from someone, they say, tell me about yourself. You don't start by listing every one of your atoms, okay? Unless you're a Caltech undergraduate, they would totally do that. But most people talk about themselves at a different level of description. That's what brings our immediate universe to life. That's part of the good news. That's good news number one. Here's the bad news. We're all going to die. If you believe this story, if you believe that life is not a substance, that consciousness is not separate from physical matter, then you believe that our existence here on Earth is temporary. We are temporary organisms, just like your laptop or a candle flame that will eventually stop. So this is a wonderful graph just to drive the point home. This is a graph made, I forget where this comes from. Well, there's a citation down here, but these are biologists who study scaling laws. So in this particular example, they've plotted life expectancy and heart rate. And there's a hidden connection in there with the mass, the body weight of the animal. It turns out that if you're larger, you live longer, but your heart beats slower. And it turns out that they exactly cancel. That along this line, you see that there's a pretty good fit here for all the different mammals that are studied. And on this line, that represents 1.5 billion heartbeats per lifespan. Whether you're a little tiny mouse or a big blue whale, roughly speaking, 1.5 billion heartbeats. Now, human beings are special because we have Obamacare, et cetera. So, temporarily. So, in a state of nature, maybe we would live for 35, 40 years. That was the typical life expectancy, but now we've improved to maybe twice that, okay? You can do the math. Twice 1.5 billion is 3 billion heartbeats. That's the human lifespan. And it's only statistical, it's only an average. Don't go home and say, I told you not to exercise because your heart would beat faster. That's not how it works. It's just an average. The point, though, is that expressing the human lifespan in heartbeats is good because, on the one hand, that's a good number of heartbeats, right? 3 billion, not bad. That's a lot, but it's not an infinite amount. And heartbeats are going by. You've squandered thousands of heartbeats since I started talking, okay? So the fact that we get 3 billion of them, and the fact that there is no overarching teleological purpose to the universe, makes us think about every one of those heartbeats, makes us take our own purposes and reasons for living and focus them on every single little bit of our lives. To me, different people react differently. To me, the fact that our lives are temporary and ephemeral and there isn't anything afterward doesn't drain life of meaning and purpose. It focuses and enhances the fact that life is the thing that has meaning and purpose. Okay, the final slide, the final piece of good news. This is both good news and bad news. This is a picture of the universe. This is the Hubble Ultra Deep Field. This is the picture you would get, the photograph you would take. You go out on a clear, dark night. You take your camera, you point it at an empty, random spot on the sky, okay? And you click the shutter, and if your camera is attached to the Hubble Space Telescope, you would get this picture. You would see that even though it is empty, if you look closely enough, the night sky is alive with galaxies, okay? Every one of those galaxies is, on average, the size of our Milky Way. So there's 100 billion stars in an average galaxy out there. There's 2 trillion galaxies in the observable universe. Undoubtedly, in one of those stars, along one of those blotches, which is just a galaxy, there's a conference going on and someone's showing a picture of us. The point of this, there's 2 points. Number one is that we are very tiny. Okay? It is very difficult to look at a picture like this, think about it seriously, and come away with the idea like, oh, I know why the universe exists. It's so that I could exist. It's hard to maintain that point of view because we're very tiny. We're really not that important as far as the universe is concerned. On the other hand, we took this picture, right? We little human beings with only 3 billion heartbeats each, doing science seriously for only a few hundred years. We used our brains, our ability to represent ourselves and the world around us and to think about it in abstract terms. And we developed knowledge in science and engineering and technology. And we used that to do this really hard thing of putting a telescope in the sky, even though it's no good in terms of winning a war or curing cancer or building a better TV set, just because we wanted to see what was out there. We did that, we human beings. We have developed the capacity to do that. We have a short period of life here on Earth to do great things, but the evidence is that we're capable of doing it if that's the choice we make. Thank you very much.
Perfect. Sean Carroll, folks. Sean Carroll.